Hi guys. Today's lesson is just a little bit more challenging, but I have total faith that you all can do it. So we talked about several different models yesterday, but I want to add on one more model, and this is the most recent model, the model that we currently use, and it is referred to as the quantum mechanical model, which was described by Erwin Schrödinger. And so it tells us the estimate the probability of finding an electron in a certain position. And so you see here in this diagram, each of these little dots represent an electron. And so what you notice is there's kind of a ring outside of the nucleus that has very few electrons. And then there's more electrons kind of in this region. And then you get into a pretty clustered region of electrons. But then as you move away from the nucleus, then there are fewer electrons out there. And so this is, and that kind of supports the model that we did yesterday, right? Like in the first energy level, there's not as many electrons because there was only 2 in that first orbit that you drew yesterday in your Bohr model. But then as you added on a Bohr model, then we have clustered layers. But then the more rings you have, only the elements that have more electrons would have electrons, out here in these levels. So like carbon, you're not going to find an electron out here. So most of the elements are going to, be found kind of in this dense region here is where you're going to find the majority of the electrons. And this is a probability over all of the elements of the periodic table. So it's not specific to any element. It's not specific to carbon. It's not specific to nitrogen. But that's kind of why we see this dense ring here. And you don't have to be able to describe that in the way that I just did, but I just kind of wanted to explain it there for you. And so like the Bohr model, this quantum mechanical model described by Schrödinger designates energy levels of electrons using numbers. And so these numbers are referred to as quantum numbers. And so they increase with increasing energy level. And so as you increase increase the quantum number, then you're going to have more energy, okay? And then the distance from the electron to the nucleus also increases with increasing values of n. So electrons out here are going to have a higher quantum number than they are in here, okay? These are going to have a higher quantum number. These are going to have a lower quantum number. These are also going to have more energy. These are going to have less energy. And that's basically what that's telling us, okay? So when we look at our energy levels, there are sub-levels in those energy levels. So our principal energy level is designated with the letter N, and it goes N, 1, 2, 3, 4. There are 4 basic energy levels, okay? The first level has 1 sub-level. The second level has 2 sub-levels. The third energy level has 3 sub-levels, and the fourth has 4 sub-levels, okay? And this is going to make more sense, so just hang with me, okay? Hang with me here. And so these sub-levels are S, P, D, and F. You're going to need to memorize those, S, P, D, and F in that order, okay? S, P, D, and F, all right? And here they are. These are the sublevels. We have these orbitals, S, P, D, and F, and they're different shapes. So depending on the sublevel, where the electron lies depends on the shape of its orbit, okay? They don't all orbit in the same way. So this is disproving the planetary model. Okay, this is a more abstract, more all-encompassing model of the electron, of the atom that we currently use now. Okay, so we're setting aside the Bohr model. Now, the Bohr model is still helpful for showing us how many electrons are there and valence electrons and all of that type of stuff. We still It's important to be able to draw Bohr models. They'll ask you to do that if you take chemistry in college. You'll have to draw a Bohr model. But for now, we're going to focus on these atomic orbitals and this Schrodinger model, okay? So the S energy level is the spherical, okay? Orbital. S stands for spherical, okay? Those orbits exist and kind of orbit in a sphere. The P, they orbit in this, it's referred to as a dumbbell shape, okay? That's what they call it, a dumbbell shape. And so the dumbbell can be in different planes though. So some might orbit in this plane. Some of the dumbbells might be going in this direction. And then some of the dumbbells might be going in this direction. That's why you see the X, the Y, and the Z here, okay? It's all a dumbbell shape, but the dumbbells are oriented different way in the three-dimensional space there. As are the spherical models. They can those you can see there's the spherical models don't orbit in a different way, but that's what the things are denoting there as well. Okay. D, you have a four-leaf clover shape. Okay. D has the clover shape orbit. And then the F is a very complex orbit. It doesn't have a special name, but it's just it's a complex orbital that can't really be described as any sort of shape, so to speak. Okay, so these are important. You will see these on a test. You will have to know SPD and F. You will have to know spherical, dumbbell, clover, and complex. Okay, so that's important. SPD and F. Remember them in that order because we're going to add on to that information in just a minute. Here you can see kind of the shapes, how I showed you that it can be turned on the axis, right? It can be looking in that direction. It can kind of be rotated on that axis. Spherical is just round, okay? D, there's our clover, and you can, depending on which way you're looking at it, it looks different. And then F is just our complex shape, okay? So, in our orbitals, the maximum number of electrons that can occupy a principal energy level is given by the formula 2n squared, where n is the principal quantum number, okay? So let's do a little math here. 2n squared. So if n is 1, 1 squared would be 1 times 2 is going to be 2. So in the first energy level, you can have 2 electrons, okay? If n in the next one is 2, then when we square it, that would be 4 times 2 is going to be 8, okay? So 8 is the maximum number of electrons in the second energy level. In energy level 3, 3 squared would be 9 times 2 is 18, okay? And then the last one is 4 squared would be 16 times 2 is 32. That's the maximum number of electrons allowed in of those energy levels, okay? Now, I'm not going to really ask that you know this right now, okay? So, probably the most important thing, aside from SPDF and those 4 shapes that you need to know to be able to complete today's task today, is the Aufbau principle. And if you were in class with me, you would not have access to this on a test. Now, I suspect, I don't know this for any reason, but I suspect that we will still be virtual when we take this test. I could be completely wrong, but I suspect that we'll still be virtual when we take this test. And so you can, potentially have this in front of you when you take a test. But let me just go ahead and tell you how I always remember to write it out, okay? So what I do when I want to come up with the Aufbau principle, because I have a hard time remembering this in my head, is I write 1 to 8 down here. 1, 2, 3, 4, 5, 6, 7, 8, okay? And S was my first letter, so all of these are going to be S, okay? In the next one, I'm going to leave off the 1, and I'm going to start with 2. And I'm going to leave off the bottom. So in every set, I'm going to leave off the top, and I'm going to leave off the bottom. I'm going to do that 4 times. The first row is going to be S. The second row is going to be P. The third row is going to be D. And the fourth row is going to be F. Okay? And so I can draw this on my paper, and that's what I would tell you to do if you were in my classroom doing it, to be able to draw that on your paper. And then you can just draw the squiggly lines through it, like is shown here. Okay? And so on and so forth. So these are our principal energy levels. I may have said it only went to 4, and that's what we did in this chart over here. But it actually goes higher than 4, okay? It goes all the way to 8, all right? We don't do a whole lot of them that go to 8 because that's going to encompass the elements that have bigger atomic numbers, okay? The bigger elements, the ones at the bottom that we don't really use, they're the ones that are going to go to 8, okay? Our smaller elements that, don't go very high up in the periodic table are carbons and nitrogens and sulfurs and chlorines, those that we kind of use a lot in the first 3 or 4 periods. They're gonna start and cut off somewhere in the 4 or 5 range. Okay, but I'm going to show you how to use this. But so what Aufbau's principle does is Aufbau's principle tells us that electrons enter the lowest energy orbitals first. Okay. So when electrons enter, they enter the 1 level, 1s, then they move to 2s, then they move to 2p, and then 3s, and then 3d, and then 4s, and then 3d, and then 4p, and so on and so forth. Okay? And you do that until you run out of electrons. Okay? I really wish that when I was in college, I tried to just remember these letters and these 1s, 2s, 3s, p's, whatever, in my head, and I didn't know a method for drawing this. I wish somebody had taught me how to draw this, and I wasn't trying to remember these random s and p's and d's, and the numbers kind of get out of order and all of that kind of stuff. So use this if you ever think you'll take chemistry in college. Then remember that Miss Brown told you how to do it, and just drop off the 1 and drop off the 8, drop off the 2 and drop off the bottom and the top each time, and you can build your own little Aufbau principle cheat sheet there and use it to answer these questions. Okay, so we're going to learn about 3 principles today: Aufbau, Pauli, and Hund's. If I remember correctly from last year, there are some multiple choice questions about these on the test, and students, even if they could do the problems, had a hard time remembering what Aufbau, Pauli, and Hund's said. So make sure that you review that when it's time. Okay? So Aufbau principle says that electrons enter the lower energy orbitals first using this scheme. Okay? Using this scheme. The Pauli exclusion principle tells us that an atomic orbital may hold a maximum of 2 electrons, okay? And that these electrons must have opposite spins, all right? We saw yesterday that those electrons like to pair up. We saw that in our Bohr models. And when they pair up, they spin in opposite directions. Basically what I mean is if one is spinning clockwise, the other one's spinning counterclockwise, okay? They spin in opposite directions. In a little bit, we're going to draw these orbital diagrams, and the way that we indicate a spin in opposite direction is an arrow up, or a half arrow up, and a half arrow down. And that shows that an atomic orbital, so this is one orbital, is holding 2 electrons, and that they're spinning in opposite directions. That's what that means, okay? Now, the last thing Hund's rule tells us when electron orbitals occupy orbitals of equal energy, one electron enters each orbital until all of the orbitals contain one electrons with parallel spins. Okay? So what that means is, I'm going to draw some lines here. And let's say we have fluorine. Actually, let's say we have nitrogen. Okay? Nitrogen has 7 electrons. So when I'm going to fill up these orbitals with electrons, I put 1 in each spot. And then I go back and put in the other spot. Okay? You don't fill them like this. That maybe wasn't the best example because it worked out the same way. But some examples it won't work out the same way. Okay? And so when electrons occupy orbitals of equal energy, 1 goes in each spot first before it starts doubling up. Okay? And that is Hund's rule. That's what Hund's rule tells us. Let's take a look at these practice problems. Before we do, there's one thing that's really important that you know. Okay? And so what that is, for S, I want you to write 1. P, I want you to write 3. D, I want you to write 5. And F, I want you to write 7. Like, tattoo this on your arm. You got to know this, okay? S is 1, P is 3, D is 5, and F is 7, okay? Each S orbital can hold 1 pair of electrons. Each P orbital can hold 3 pair of electrons. D can hold 5 pair, and F can hold 7 pair of electrons. Okay, like they're your winning lottery numbers. You got to know these. Okay, 1, 3, 5, and 7. So, when we write our orbital notation, what we have to know to start these problems is how many electrons there are. Okay, so phosphorus, it has atomic number 15. So that means if it's a neutral atom, there are 15 electrons. Okay, 15 electrons. So when we go back and look, when we go back and look, we're going to fill 1s, 2s, 2p, 3s. Okay? So we're going to write 1s, 2s, 2p, 3s. Okay? That's how it's going to feel. All right? Now, for the S's, we just draw one line because it holds 1 pair of electrons. Okay? For the P's, we have to draw 3 lines because it holds 3 pair of electrons. So I'm actually going to change this one to 2p. 2p. Okay? So, and then the next one was going to be 3s. Okay? And so we're going to fill these up, and we're going to fill them in a way that our spins are parallel. Okay? So we fill 1s first. Okay? So there's 2 electrons. And then we fill 2s. So there's 2 more electrons. That's got 4 of our electrons. And then we fill 2p. Now, we've got 3 different p orbitals. So when we're filling p, we have to fill 1 in each first. Okay? And then go back and do the second one. We didn't do that in 1s and 2s because they were different. Okay? But we have to do that in the p's because they're all in the same orbit. Okay? Okay, so now we have 2, 4, 6, 8, 10 done there. So now we've got 3s, so we'll fill it. So that's 12. And then after 3s, we go to 3p. Okay? So we'll write a little line there just to keep us straight. 3p. And so that's our 3p. Now, we've got 2, 4, 6, 8, 10, 12. We need 3 more. And so this is a case where it would make a difference. Notice that I didn't do like that and leave that third one blank. That would be incorrect. Okay, don't do that. You have to put 1 electron in each orbit first. Okay, and so this is the orbital notation, or I think on your homework it's referred to as the orbital diagram. Okay, for phosphorus. That's how you do it. Okay, so when we write our electron configuration, we write it out as 1s2, because there's 2 in there, 2s2, again 2 in there, 2p6, okay, because there's 6 in there, 3s2, 3p3, because we've got 3 electrons in there. And when you add these numbers, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 3 is 15, it should get you that, okay? It should get you the number of electrons that are in that element, 15 electrons, okay? Now, let's try it for nickel. I'm going to have to erase all this, okay? You see that let me just touch on one more thing again. You see that in S I did 1 line, in P I did 3 p orbitals. If I had gone up to a D, I would have done 5 lines to fill those orbitals that way. If I'd gone up to an F, I would have done 7 lines, okay? I'm going to explain that a little bit more thoroughly in a minute. But let's look first at nickel. Now, I'm going to have to close out of this to be able to delete it. Okay, there we go. So let's look at nickel. Nickel, it is a little bit bigger. It has 28 electrons, okay? So I'm going to write out 1s, 2s, 2p, 3s, 3p, that's the ones we did earlier. Let's go back and consult our thing. After 3p, it goes to 4s and then 3d, okay? So let's write those in. So 4s and then 3d. And that one is d, and so d is 5, remember? So we have to put 5 lines here. There's 5 d orbits, okay? And so now we're going to fill in. And I may not have to go that high. Maybe I need to go more. But let's get started here and see if we can make it. Okay? So 1s, I'm going to fill that one up first. Then 2s. 2p, I'm going to add 1 to that. And then come back and add the second one. 3s, I'm going to fill it up. 3p, I'm going to add them in as 1. And then come back. Oh, that's kind of messy. 4s, I'm going to fill that one up. Let's count and make sure how many we have so far. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, so I need to do a few more. So 21, 22, 23, 24, 25, 26, 27, 28. Okay. And this is the correct orbital notation, or as I said previously, maybe better called an orbital diagram for this, okay? Now, let's write the electron configuration. So we're going to write this out, 1s2, because we've got 2 there, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Okay, 3d8. 6, yep, 7, 8. All right. And then, you could go back and add these up. 2 and 2 is 4, plus 6 is 10, 12, 18, 20, 28. And so it appears that I did that correctly. Okay, that is the correct electron configuration. All right. Now, you have 2 more to practice, but before you do that, I want to show you just a bit of a shortcut. Okay. So, pull out your periodic table if you don't already have it out. I don't know why you wouldn't. We use it like all the time. Okay. So, this right here, I want you to think of that as the S block. Okay. This right here is the P block. This is the D block. And these down here are in an F block. Okay, which actually these, we haven't really talked about this much, but these actually go in right there. They just couldn't, it didn't fit with the periodic table trends, and it kind of made the table too wide, and so they didn't put them in there, and so they're kind of drawn down below. But if you don't get to, if your periodic element has less than 56 electrons, you won't get to the F block. F block is going to start at 57, okay? So I will give you a couple in the F block just to challenge you and make sure you know how to do them. But for the most part, our elements are not going to be in the F block, okay? So I'm going to just pick a random element. Let's say selenium. It's kind of a big one, okay? And without drawing all that, if you didn't ask me to give the electron diagram, I can look at my periodic table and I can tell you the electron configuration for selenium, okay? What you need to know is you need to know your period numbers, okay? Now, one thing that's a little bit tricky about the D block is it's the number -1. And the F block, it's the number -2. And I'll explain that more in just a minute, okay? So, let's try to give the periodic electron configuration for selenium, okay? So, I have to fill the S block first. So, that's going to be 1s2. I'm going to write it down here, 1s2. And then it's going to be 2s2. Notice I'm filling that S block, 2s2, okay? Then I'm just going to work my way through all of these elements until I get down here to selenium. So then I'm going to go to the P block. I'm still in row 2, so it's 2p6 because P has 6. 1, 2, 3, 4, 5, 6. That's where it gets those 6. That's where this S gets the 2, 1, 2 elements here, okay? And then we're going to go to 3s2, and that's going to take out those. Then we're going to go to 3p6. Notice that I'm in 3 because I'm in row 3 here, okay? Then we're going to go to 4s2, all right? Now, here's the tricky part. Remember I said D is the number -1? So it's not 4D, it's D is the number -1, it's 3D, okay? 3D, 10, and if you look back at your notes, after it goes 4s2, that's exactly where it goes. It goes to 3D, 10, okay? Let's go back over here. All right. And then we're going to jump. We're back in the P, so we're going to still use our 4 again. 4P, 1, 2, 3, 4 gets me to selenium. 4, okay? And that is the electron configuration for selenium, okay? Now, let me explain a little bit about this F block here, okay? Let's say we were trying to go to promethium, element 61, okay? So we would keep going. I'm not going to write it. Well, I guess I'll just go ahead and write it all out for a promethium. So to keep going for a promethium, it wouldn't end in 4p6. Promethium would go, 4p4 like selenium. Promethium would keep going, except it would be 4p6. And then it would go 5s2. And then it would go 4. Remember, we dropped down 1. So we're actually in 5, but because it's a D, it's going to drop down 1. 4d10. And then back up to 5p6. I'm running out of room. Okay. And then 6s2. All right. And then I'm going to promethium, which is actually right here. Okay. And so then it's going to jump down here, and it's going to go, it's in row 6 technically, because remember these are supposed to be up here, but we have to do our number minus 2. So it's not going to be 6f, it's going to be 4f. And then we're going to go 1, 2, 3, 4, 5. 4f5. I should write 4f5. Okay. So promethium would be 1s2, 2s2, 2p6, 3s2, all those, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f5. Okay? And you saw how we did the number, the row number, minus 2 once we got to the f orbit. All right? Now, I know that was a lot. If you have questions today, bombard me. Okay? You have 2 to practice right now. Also, before I forget this, on your assignment today, there's a front, and then there's about 4 or 5 questions on the back. Don't do the back. I repeat, don't do the back. Just do the front of the assignment today. Okay? But right now, I know this lesson's gotten a little long, and I apologize. Do your you try it problems, and then come back, and I'll go through them with you. All right, let's take a look at these you try it problems. So the first one is carbon. So I looked at my periodic table. I found that carbon has an atomic number of 6. So it has 6 6 total electrons. So I filled 1s first, and then 2s, and then I started in the 2p orbital. And so I only got 1 in each of the 2p orbitals. And so that is how I filled it up. And so when we write the electron configuration for this one, 1s2, 2s2, 2p2, and 2 plus 2 plus 2 is 6. And so I have added those up and done that correctly. Okay. Now for argon, I filled 1s and 2s, and then I did my 2p's one at a time. Okay. 3s, and then my 3p's one at a time. And that gave me all 18. So the electron configuration for this one would be 1s2, 2s2, 2p6, 3s2, 3p6. And again, let's just look at these easily on our periodic table. So I did carbon and I did argon. So to do carbon, this is my S, okay? And this is still included in S because it's helium is not, nicely sitting right here like all of the other elements are. Because it's a noble gas, and so it needs to be over here with the noble gases. And then this is our P level, okay? And then this is our D level, which we didn't actually get to, and then our F level down here. So for carbon, it was 1s2, 2s2, 2p, 2, okay? And that should be exactly what we had written on the other page, okay? For argon, it was 1s2, 2s2, 2p6, 3s2, and 3d10. And I think that is also what we had written. I'm sorry, I don't know why I said 3d10. There's not even 10 electrons there. 3p6. And that's exactly what we had written over there. We don't get to D until we hit number 21 or greater, because that's when that d orbital starts. Okay, so 3p6. All right. And so go ahead and give this a try today. If you have any trouble, let me know. Please, feel free to reach out, and I'm happy to help you. And you all have a great day.